One of the reasons we really care about shear in beams is because of its effect in built-up composite members. And when I say built-up composite members, what I mean is beams that are made from a bunch of different parts, or can even be made of the same part, just fastened together in some way. So, for example, we might take wood beams, right? We might take a bunch of wood beams and glue them together. This is a product you can find at like Home Depot or wherever you buy lumber. Often abbreviated as glue lams, which are glue laminated wood members. So it's just a bunch of wood glued together. Right, this might be your cross-section view. I can make it a little more 3D. There we go. So you could have sections of wood that are glued together where the shear would affect the sections where they're glued, right? You don't want the shear to break the glue and then your boards snap in half, right? Or snap apart from each other. We also see these built-up composite members in fasteners, right? So in building your chair, for example, you want to build an office chair or build a little chair for yourself, you might hold that together with bolts, right? So here's a metal plate, and it affixes to your chair with some bolts. So we might see bolts or rivets, nails, all those types of fasteners where you're just connecting one piece of material to another piece of material. Another one that we see a lot in the same vein would be welds, right? Things that are welded together. So you might have, one piece of metal that gets welded to another piece of metal, make you a nice little T-beam or an I-beam. So you could have welds, bringing those two separate things together. Or another one, screws, nails, screws. So lots of different types of fasteners, right? The general group that we would call these are called fasteners. Did I spell that right? I don't think I spelled that right. Hold on. Fastener. Nope, I spelled that super wrong. Fastener. So these are fasteners. They are what connect two materials together, right? We see them all the time in everyday life. So this is why we care about shear. We use these all the time, and it's really important to know that we're not going to transmit that shear into the bolts. Like we talked about at the very beginning of the semester, we did average shear stress calculations on bolts and things like that. Now we want to find the exact shear stress that's being put on these bolts or rivets or nails, whatever fasteners that we're using, because we want to make sure that they're not going to fail, right? We don't want these bolts to break, get all of the shear stress, and then they fail under that shear stress that the beam is being put under. So as we're designing these, right, typically the way we think about designing beams is first we want to think about the overall shape, the cross-sectional shape that we want our beam to be in, and what materials we're going to make it out of, right? We've talked a lot about material properties that give you these like stress strain limitations, these moduli of elasticity, all these properties that you can get from different materials, and we can select a cross-sectional shape that meets our function needs, our serviceability needs. Like for example, if you want to design a catwalk that runs above a stage, you would want a different cross-section than, say, building a floor, right? They would be slightly different. They have different use cases that you would want to consider. And of course, cost, right? We do take cost into consideration when we're picking our shape and our materials. But the secondary thing we design for is these fasteners, right? Selecting how we want to glue these things, attach these things, fasten these things together. If it's properly designed, then our beam should act as one single unit. Even though it's multiple composites together, it should act as one single unit. So it shouldn't be like when a screw is coming loose on your chair and it can kind of jiggle and you hear that they are coming apart, right? They become like two separate pieces that are barely being held together. We don't want that. We want them to act as one single unit. So that's what we design for. And how we design for that is something called shear flow. So shear flow is how we design these connectors, right? These connectors have to transfer force in the longitudinal direction. Connectors or fasteners must transfer that force. Transfer force. So that shear is going through, it's hitting those bolts, and those bolts are taking on the force, right? They are transferring the force. So to design the connectors, we design it based on loading from shear flow. And shear flow is represented by the lowercase letter q. This is how I write my q's. So it is not the same as this q that we've been calculating for transverse shear. It is not this q. It is a different q. This is shear flow. Lowercase q is shear flow, and it typically has units of length per distance. So like a Newton per meter or a pound per foot, kip per inch, that kind of thing. Because Q represents the length per unit force along the beam. Or the force per unit length. Sorry, I said that backwards. Q is shear flow is force per unit length along the beam. And the way we calculate that is we kind of get two equations that work together to calculate this shear flow. So one is our shear flow equation, Q, lowercase q, equals V, our shear force, times Q, uppercase Q, our first moment of area, over moment of inertia. Now you'll notice it looks a lot like our shear stress equation, right? Our shear stress equation was VQ over I times T. Now this thickness term is not in there. That width term is not in there. This is a force per unit length that we're getting. So not a stress that's a force per area. Instead, this is a force per length. This is our shear flow equation. All the same variables, just no T on the bottom. So this is our shear flow. And with this shear flow equation, this works with our fasteners. We can find our fastener spacing from this force per unit length. So we can write this as our Q is the force over the distance, this distance S between different fasteners. So if I had, let's say I had this wood beam, and I want to nail it to this other wood beam, make myself a little T-beam. So I've got nail, 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 so on and so forth. Then my, let's do it in green. My S is my distance between these two bolts, or nails, or whatever they are. This is S, the distance between those. And F is the amount of force that the bolt is getting. That is, they call it shear force a lot of the time. You'll hear it as shear strength. So F sometimes you'll see as shear force. It's not the same as V. Shear force or shear strength. It is the shear force through the bolt or fastener or nail, you know, whatever fastener you're using. It is the force supported by the fastener. It's how much that bolt can handle. So it might say like, oh, this bolt can handle 1,000 pounds of force before it breaks. So that'll tell you, oh, that my shear flow needs to be lower, right? Or I can design my spacing based on the shear flow that I calculate here. And I know that they can only handle 1,000 pounds of force. So I want to space them out so that they handle less than 1,000 pounds of force for every bolt, right? I don't want them to go to failure. So shear force or strength through the bolt, supported by the bolt. And then S is the spacing between fasteners along the length of it, right? Because it's Q is force per unit length. Q is force per unit length. So it's one of the ways that we can use these calculations together to design beams, this shear flow concept. Again, very similar in equation to shear stress, but is not a stress. We call it shear flow. It's a force per unit length. And it might make a little more sense in application. So let's go ahead and take a look at an example. All right, this is going to be a pretty big, long example, so settle in. Here we've got a beam constructed from 3 boards, and we want to determine the max shear that it can support if the allowable shear stress is 400 psi. So immediately I'm going to start just writing down some of those things that they give me. So my allowable shear stress is 400 psi. We have these 3 boards. We're given the cross section over here on the left. And we want to find V. We don't know what V is, right? We don't know what the shear is. We know shear stress. We don't know the shear. And we're only given the cross section, no beam loading or anything, just the cross section. And then our second portion says, what is the maximum allowable spacing S? So that would be the spacing between these nails here. What's the maximum allowable spacing S of the nails if each nail can resist a shear force of 400 pounds? So each nail being able to resist 400 pounds, that shear force that they're talking about here is the shear force for the nails. So that would be the F term that we've just talked about. But we'll come back to that. Let's come back to that and instead go ahead and look at just the first portion, finding the max shear V that it can support. So we know we have a relationship between shear stress and our shear, right? Throwing it back to our transverse stress, our last video, last lesson, VQ over IT. So all we're going to need to do is rearrange this equation and find the ingredients we're missing, right? So they gave us the allowable shear stress. So we'll just have to find our uppercase Q, right? Our first moment of area, moment of inertia, and the thickness at the point of interest. And since it asks for the max shear, we know that max shear occurs at the centroid. So we'll notice that very inconveniently, this beam is not symmetrical, right? It has a longer top. It is a 10-inch board on top versus a 6-inch board on the bottom. So the centroid won't be right in the center. We're going to have to calculate the centroid. So that'll be the very first thing we do before we go ahead and find our moment of inertia and our Q. And our thickness as well, right? We can't actually determine the thickness till we know where that centroid is. We don't know where the max shear is because we don't know where the centroid is. So let's go ahead and do that calculation. Our centroid is sum y tilde a over sum of areas, and doing that for each cross section or each rectangular area here. So I'm going to start from the bottom and work my way up. So the centroid of our bottom shape here, it's halfway through the 1.5, so this is 0.75. So 0.75 inches times the area, which is 6 times 1.5 inches, plus our next shape has a centroid halfway through 12 is 6, right? And then 6 inches, that is 1.5 inches off the ground, is 7.5 times the cross-sectional area for that one is 12 inches by 1 inch. 1 inch times 12 inches. Plus our top board has a centroid at 0.75, and then add everything below that. So 0.75 plus 12 plus 1.5 is going to give me 14.25. 14.25 times the top area. So 10 times 1.5 inches. Divide all of that by all the areas. 6 times 1.5 plus our center is 1 times 12 plus the top board, 1.5 times 10. And all of that is in inches, so it's going to work out to give our centroid location in inches. And that gives me a centroid of y bar equals 8.625. And that's up from the bottom. Since all of these centroids I was measuring up from the bottom, that is somewhere, let's say right here. Right here's our neutral axis, where y bar is 8.625 inches off the ground. So that's this distance here. From the bottom to the neutral axis is 8.625 inches. Or if you want to relate it to the top, we can get this relationship too. It is 6 point, I thought I had it written down somewhere. 6. Maybe I don't. Alright, well, that's okay. I can punch it in my calculator real quick. Let's see. It's what is it? 12 plus 3, it's 15. 15 minus 8.625 is 6.375. 6.375 inches for our distance from the top to the neutral axis. Just in case we want to refer to it either way, helps to have both of them there. I guess I apparently only wrote it the one way, but it can be helpful to have both numbers there. So great. So now that we have that, we can find both the moment of inertia and Q. So I'm going to go ahead and start with moment of inertia. That's just what I feel like. And I'm actually going to do this one in the tabular method, make a table for this because there's 3, right? We usually, like, if there's 2 composite areas, I'll usually just do it with the equation, but with 3, I think I'll use a table just so I don't get lost. So the way that I like to do moment of inertia when I do this table method is I like to do every shape. So I'm going to say this is the top shape, this is my 10 by 1.5 shape. And then I like to do, here's the middle shape, the 12 by 1, I don't always draw them in as pictures. Sometimes I just label them like shape 1, 2, 3. But it's totally personal preference. 6 by 1.5. And then in this table, I like to have the basic moment of inertia equation. So 1/12 base height cubed, since they're all rectangles. I like to put the area, and d is y tilde minus y bar, the difference from the centroid of each shape to the overall centroid, and AD squared. Because then what I can do is I can come to the bottom here, and I can sum my first column and my last column, and that will give me my moment of inertia. All right, so let's go ahead and do these for each of these. For this shape, 1/12 base is 10 times height is 1.5 cubed. Plug that in my calculator, and I get 2.8125. Next shape down, 1/12 base is 1, height is 12 cubed. If I plug that into my calculator, I get 144. Then my third shape, 1/12 base is 6 times height is 1.5, and that gets cubed. It gives me in the calculator 1.6875. And then my areas, I have 10 times 1.5 is 15, 1 times 12 is 12, 6 times 1.5 is 9. And then for my D's, I'll need to find the centroid of each of those, which we already have. We found the centroid for each of those was, for my top guy, we said it was 14.25. For my middle guy, he was 7.5. And for my lower guy, he was 0.75. And I want to subtract from the main centroid. So distance from the centroid, the neutral axis, to each of those. So 14.25 minus 8.625, 7.5 minus 8.625. And it's okay if these numbers are negative for your distance here. Really, you do absolute value, or it doesn't matter because it's squared. It comes out as a positive anyways, right? This D term gets squared here in the next column. So it really doesn't matter if you leave these as positive or negative. I just make them all positive because I know it gets squared. It works out either way. So this difference is 5.625. Next one is 1.125. And that's just from punching each of these into my calculator. Centroid of the individual shape minus centroid of the overall shape. Last one is 7.875. And then finally, I'll just multiply across here, right? I take this D term, I square it, and then multiply by 15. So 5.625 squared times 15 gives me 474.61. 1.125 squared, right? Don't forget to square these guys. Times 12 is 15.19. And 7.875 squared times 9 is 558.14. My last step is just add the numbers down the first and last column. So 2.8 plus 144 plus 1.6 gives me 148.5. Then add these, my last column, down the column. 474.6 plus 15 plus 558 gives me 1047.94. And then all I need to do is add these two numbers together, right? Our moment of inertia equation, I equals ix plus ad squared. So we already did all the heavy lifting of adding everything else. 148.5 plus 1047.94 gives me a moment of inertia 1196.4 inches to the fourth. All right, and I'm just going to I'm going to bubble that out so that I can come back and find it, because I know that this is going to be one of my ingredients in here, right? I know I need it for this. So I have I. I'm looking for V. I have shear stress. T, we can go ahead and find T, right? T is the thickness at the point of interest. Our point of interest is the neutral axis. So that would be our thickness right in here, right? Which is this 1 inch. So T equals 1 inch. All right, got that guy. So the last thing that we need is that Q term. And this guy can be a little bit tricky because it's not always obvious what to use when you're given something that has a different top and bottom like this. So in this case, what I would do is do both. Do both your top and bottom Q. And what I mean by that is going ahead and calculating what is my Q value if I look at the cross section, at the top half of the cross section. Right, so here's the top half to the neutral axis. Looking at this to find Q. This would be the top version, or do the bottom version, right? And when I say or, I actually mean and. Do both of them to find which one gives you a higher value of Q. Because you want a higher value of Q to get your max stress. So this would be Q bottom. I'm going to go ahead and skip this and just do the one that I know is higher. So I know that Q top is higher just from working them both out. So I'm only going to demonstrate how to do the top one, but it would be a good idea to check both to see which Q is higher. And sometimes your Q works out to be the same, especially if they're symmetrical, your Q is going to be the same. So you usually only need to do one portion, but it's good to check. We're going to go ahead and get rid of this one. The larger Q is given from the top section here. So this is our Q setup. Right, we have 10 on top, 1.5 on the side here, and then this distance is 6.375 minus the 1.5 inch. So this distance is actually 4.875. Right, cuts through at the neutral axis there. That's what we're measuring from. And then this thickness is 1 inch. All right, so we're going to look at this Q, calculate the Q for this entire top portion to the neutral axis. Again, Q, top half of our centroid equation, y tilde times A. But now this time measured from the neutral axis, right? So it's different from what we worked out above here because it's being measured from the neutral axis, whereas these y tildes times a's were being measured from the bottom and for the entire shape, right? So it's only for this top area. So let's look at my skinny rectangle first. The lower rectangle here. Y tilde, my centroid. It's right in the middle here, which is half of this 4.875 value. So 4.875 over 2, whatever that comes out to be, it's just halfway up here. And then multiply by the area. So 1 inch base times 4.875 height. That's my bottom rectangle. And then we'll do the top rectangle. Right, cutting right in here halfway through the 1.5. So we know that that's 0.75. Oh, I forgot to add. See, it's easy to make these little mistakes like that. Right? It's not this 0.75 value. You have to add this area below it too. So it's actually 0.75 plus everything beneath it. 4.875 times the area for our top shape. So times 10 times 1.5, and I'm a little bit out of room, so I'm just gonna write 15. 10 times 1.5 is 15, that's the area. Plug all of this into my calculator to get this Q value of 96.26, and everything was in inches, so it works out to be inches cubed. Whew, there we go. We've got Q. We have everything that we need in this shear stress equation to go ahead and solve for the shear value. Right, find what that shear is. So we've got 400 psi equals shear times Q, 96.26 inches cubed, divided by our moment of inertia. What was it? Where is it? Oh, it's right in front of me. I put a big blue circle around it. You'd think I would be able to find it. 1196.4 inches to the fourth. And the thickness value, that T value, which was 1 inch. So I go ahead and plug this into my calculator. I got to do some rearranging, right? I got to multiply 400 times 1196 divided by 96. And that gives me a shear value of 4972 pounds. Right, all of these inches all canceled each other with the PSI for pounds. 4,972 pounds, or 4.97 kips, if you're so inclined. This is our max shear that we can subject this group of 3 boards to, right? To not exceed this allowable shear stress. The max loading, if we wanted to draw a shear in moment diagram, there could not be a shear greater than 4,972 pounds. So that was just the first part of this, right? They ask us in this second question, what is the max allowable spacing S of the nails if each nail can resist a shear force of 400 pounds? So now this is asking us almost an entirely separate question here. Right, we want to find that spacing, and in order to find the spacing, we need to do shear flow. So for our shear flow, I'm really out of room here, but our shear flow is VQ over I. So thankfully, we can use this same moment of inertia. It's a property of the cross section. We can use this shear that we just found. So it's very handy that we did find this shear, because we could not have done the problem without finding this shear first. But when we take a look at this cross section, I'm going to move all this moment of inertia calculation. We have the number we want. But when we take a look at this, uppercase Q, right, our first moment of area, we're finding the max allowable spacing of the nails. We're looking at where those nails are interacting, right? So the key with these spacing problems, the key with these shear flow problems, is that if we're looking at the cross section, here's the cross section, Here's the nails going through. Right? Nail, nail. We're looking at this interaction here, the interaction between the boards. That's our point of interest. That's the point where the nails would fail. So when we're looking for uppercase Q, when we're looking for that first moment of area, we have two different points of interest, right? So this is our first point of interest, Q for the top, and this would be our second one, Q for the bottom. Right? We've got two sets of nails going on. 3 boards, they have to be held together by nails on the top and nails on the bottom. So since they have those nails on top and nails on bottom, we have 2 different Qs here that we're going to need to calculate. We found our shear value of 49.72, moment of inertia of 1196 inches to the 4th. Now we just need to separate, find for the top nails, find the Q, find the shear flow, then find the spacing, and then do the same thing for the bottom. So for the top here, here's my top portion. Again, point of interest is this interaction right here. So we're looking at all of this area above where the boards are joined. So this area here, above the neutral axis. This distance, we just said, what was this distance? 4.875, 1.5, and then this top thickness was 10. So Q top, right, our first moment of area for the top, y tilde a, is going to be 4.875 plus 0.75 times 10 times 1.5, right? It's literally just the orange portion of that Q equation that we had done earlier. So it is a different Q value. This Q value is 84.375 inches cubed. So that's our most critical part. Our most critical part is don't make the mistake of using this Q value that we used before. You need a new Q value at this intersection point. And then we can calculate the shear flow. So shear flow equals V 49.72 times Q, the new Q, 84.375, all over the moment of inertia, same moment of inertia, 1196. Punch that in the calculator, and it spits out about 350 pounds per inch. Pounds per inch, right? We had pounds times inches cubed over inches to the 4th gives us the force per length, pounds per inch. And then the very final step here is using that Q. Let's do it in blue. Q equals force over spacing, the force that they can handle over the spacing. So we have our Q value. They gave us the force that the nails can resist, this 400 pounds of shear force. So our spacing is going to be F over Q. Spacing is the 400 pounds that each nail can handle over the 350 pound shear flow. Gives us a spacing of 1.14 inches. And again, this is a maximum spacing, right? If we put less space between them, then each bolt will be taking on a little bit less force. So this is the absolute max spacing between these nails, right? This is what our problem originally looked like up here, where we have these nails. S is the absolute max spacing of 1.14 inches. Now we do have to do this same process for the bottom, right? Our bottom nails may not have the same spacing. It's a different board. It's a different board connection. It's a different geometry. So we need to take a look at that different geometry. Let's go ahead and do it over here to the right and calculate our shear flow for that. All right, so now we're looking at our shear flow for the bottom. So our neutral axis will be at the top. Our line comes down, and then we have that little section here, 6 inches, 1.5 inches, and then we know that this total distance was 8.625. And again, for the Q, only the area past the point of interest, right? Away from the neutral axis. So this is our point of interest. It's going to be all of this area below it. So Q y tilde times A. Our y tilde, it's at this 0.75. So that's 0.75 away from this 8.25. So this distance here is 8.625 minus that 0.75, which is 7.75? Is that right? 7.9, 7 point, it's 7 something. I'm just gonna leave it. I'm gonna make the calculator do it. So y tilde 8.625 minus 0.75 times the area, and it's just this lower area, 6 times 1.5. When I punch that in the calculator, I get a Q of 70.875 inches cubed, right? So a lower Q value for the bottom. But I go through the same process of finding this shear flow, where Q is 4972 times this new Q value of 70.85 over 1196. So I get a Q, since my uppercase Q, right, my first moment of area was slightly lower, I do get a shear flow that's slightly lower of 294.5 pounds per inch. And then again, I can plug that into that S equation. S is F over Q. So S is 400 over 294. So the spacing for the bottom nails is going to be 1.36 inches. Right, so they're dealing with a little less force there. A little less, 1.36 inches. They can be spaced out a little bit farther on the bottom planks. These bottom nails, this bottom, 1.36 inches. As top would be 1.14 inches. Different spacing. We would have to have the correct orientation, make sure that we have everything in there, but now we know exactly how we would have to design this beam. And, if we wanted to be safe, we could just say, top and bottom, give all of those nails 1 inch apart, top and bottom, right? Just make it really simple. They'll be close enough together that they won't overload, right? They won't fail at the nails. Of course, it would be overkill, and if this beam is 20 feet long, you'd be using a significant amount more nails, so you may not want to do it that way. But, just having those options, knowing what you need, and then being able to make the right design decisions for you is such a big part of engineering. One last thing that I do want to mention on this is that if we had, for example, we didn't have a single row of nails here, but instead we had, this is so messy, I'm running out of room here. If I had the board and the board connection, but instead I had two sets of nails next to each other. So here's a nail and here's a nail. Boom, boom, that connected in. Two nails, right? This was a case we did look at way, way back at the beginning when we were looking at shear stress. How this affects our shear flow would be by dividing it by however many rows you have. So your Q value would actually be Q over 2 for this case, right? So you would have Q over 2, that would give you a Q value of 175-ish. And so your S would double, right? Your S for your top value could be 2.28 instead of 1.14 inches. So it doubles the amount of distance you have because you have these two nails next to each other. And if you had 3 nails next to each other, it would be Q over 3. So that's just something to keep in mind in case you encounter things like that. You can get a little bit more spacing with more rows of nails next to each other. Just something to keep in mind. Let's go ahead and take a look at one last example. In this last example, we have 3 boards nailed together again. As we can see, it's nailed with a single row of nails on the top and a single row of nails on the bottom here in our cross section. And it's made of wood. We have this beam made of wood, and it tells us that it has the wood has an allowable shear stress of 1.5 megapascals. So tau allowed is 1.5 megapascals, and also has an allowable bending stress of 9 megapascals. So throwing it back to several videos ago now with beams and allowable bending stress, right? Our allowable bending stress, moment times C over moment of inertia. So allowable bending stress of 9 megapascals, and that the nails are spaced at a distance of 75 millimeters and have a shear strength of 1.5 kilonewtons. So that spacing of 75 millimeters, 0.075 meters, and that they have a shear strength of 1.5 kilonewtons. So a shear strength, it tells us that this is the max limit for these nails, right? That the allowable force in the nails is 1.5 kilonewtons, 1,500 newtons. And we want to determine what is this allowable force P that can be applied. So this P right here, what is the maximum value we can put in for P and not exceed any of these allowable values, right? So this is kind of a big, tough problem, right? That's bringing together all of these concepts that we've been talking about for the last couple weeks since we've been talking about beams. So there are 3 cases here actually that we're going to need to check to see what our value of P can be, right? And we want to find our limiting case. Where is our P the lowest? Like what is the limiting factor that's going to be the lowest, or I guess the maximum permissible force? So our lowest value that we calculate is going to be our limiting factor. And it can be hard to tell when you have all of these cases that you need to check, but the easiest tell is that if it tells you it has an allowable shear stress, allowable bending stress, it doesn't say allowable shear strength, but it gives you that shear strength is a cap, it's a maximum. Anytime you have these maximums, they're usually competing for different things, right? Usually they are different ways to calculate something, similar to how in torsion we had angle of twist versus the torque equation, where sometimes you had to check both of those to see which one gave you a limiting case for your diameters. This is the same idea. We want to see which one of these values is going to be the limiting case for our load P. So I know it can be it seems like a lot of steps, right? There are 3 different ways we have to go about it, 3 different ways to calculate P. But I want you to go ahead and try this on your own. See how far you can get with maybe just one of these allowable cases. Try these out, see if you're comfortable with them, and then we're going to go through together how you would find each of these options. So it's kind of a recap of things that we've done before and introducing some of this new stuff with the shear flow. So go ahead and give that a try, and then we'll talk about it. All right, so again, we have the 3 allowables here: allowable shear stress, allowable bending stress, and allowable shear strength, right? A maximum shear strength. So let's go ahead and look at those 3 options here. So option 1, to limit P, option 1, bending, say bending moment, bending stress, let's say bending stress. Bending stress. Option 2, shear stress. And then option 3 is the shear flow option, or the fastener's limitation, that shear strength limitation. So I'm going to just call this shear flow Q, or you could call it shear strength F, whatever you want to call this. Shear strength F, limited by F. So our bending stress, throwing it back to a few videos ago, we talked about the bending stress as the normal bending stress is the moment times the distance to the outer edge over moment of inertia. For our shear stress, that's where we had our shear times Q over moment of inertia times thickness. And then finally, with this shear flow, we know that F equals QS. And we also know Q equals VQ over moment of inertia. Shear flow is V times Q over moment of inertia. So essentially 3 different equations, 3 different ways we're going to try to solve for P. But we're still missing a lot of the ingredients that we need for each of these use cases, right? So 2 of them need the Q value, 2 of them need the shear value, the first one needs a moment, and all of them need moment of inertia. So you can kind of pick how you want to approach this first, whether you want to go through the geometry, or since you know you need a shear and a bending stress, or shear and moment, you can start with a shear and moment diagram. So I think that's how I'm going to start this one. I'm going to start this one by making the shear and moment diagram to know how my P kind of shakes out in relation to everything. So if I look at this guy, look at my diagram here, I'm actually gonna move this. I'm gonna move option 1 over here. Come back to him later. I go ahead and look at my shear and moment diagram. So P hits right in the middle of this beam with a pin at A and a roller at B. And since this is perfectly symmetrical, I know that each of these reaction forces are going to take on half the load of P. Right? P over 2, they each get half of the load of P since P is right in the center. Kind of throwing it back to very basic statics, which you could also determine if you actually do the statics and you take a moment about A, you would find you'd have P times 1 and B times 2, and so you'd get B as P over 2. But you can also just do it by symmetry, and you can say, okay, I know that these reactions are P over 2, which means if I do my shear and moment diagram, my shear diagram is P, it goes up by P over 2. It goes up by P over 2, it is constant at P over 2, pushed down by P, and then a constant negative P over 2. P over 2, pushed down by P, negative P over 2. All right, pretty much as basic as it gets for a shear and moment diagram, but it does let you know that the shear, the max shear that we're going to encounter, is P over 2. So I can do the same deal with my moment diagram. Here's my moment diagram. And remember, moment is the integral of shear, so that's just area under the curve. So for my first section, area under the curve would be P over 2 is the height, and then the distance is over 1 meter. So P over 2 times 1 is P over 2. So in this one, I've got my moment goes up to P over 2. And then I have a negative P over 2 as a constant for this. So it's going down, right? My area here is negative P over 2 times 1. Go down by negative P over 2. Down to 0. So my moment also, very coincidentally, very conveniently, the maximum moment I'm encountering is also P over 2. So now I can make these substitutions in each of my options, option 1, option 2, option 3, for P. P will now be included in each one of those equations, so we can solve for P. Now we just need to get all of this other junk that we need to plug in there. And since moment of inertia seems to pop up in all of them, we'll go ahead and calculate our moment of inertia. Thankfully, this guy is symmetrical, right? His about the top and bottom. He's perfectly symmetrical, so his neutral axis is going to hit right in the center there. This is 250, so his neutral axis hits at 125 millimeters. 125, that's our y bar. All right, let's find our moment of inertia. Is 1/12 base height cubed plus AD squared, sum of each of those for every rectangle. But we notice the top rectangle and the bottom rectangle are the same, and they're equidistant from the center. So we can actually just find it for 1 and then use it again, right? Multiply it by 2. We have 2 of the exact same boards on top and bottom. So we're going to have, let's do our top board. 1/12 times the base is 100 millimeters, height is 25. So base of 100 times 25 cubed, plus the area of that board, 100 times 25, and then the distance from the center of from the center of my rectangle to the center of my overall shape. So this distance here, let's see, the distance from the top would be 12.5. So 125 minus 12.5 is 112.5. 112.5 squared. And then there's 2 of those, right? So you take this rectangle times 2 for the top and the bottom. And then we'll do that middle rectangle there. And very conveniently, this middle rectangle, aligns with the center of the centroid, right? The center of this rectangle is also the same as the center on the centroid. So there is no AD term that we have to worry about for that. The AD term would just be 0 because distance to the centroid is 0. So we only need to add that 1/12 base. What's the base on that? 25 times a height of 200 cubed. So that my moment of inertia works out to be 8.021 times 10 to the 7th millimeters to the 4th. Excellent. So I have something to plug in for V. I have something to plug in for M. Actually, let's go ahead and highlight all of those, right? So we've got our thing for M. We've got our I. We have V. Now we just need these other few ingredients. So the Q's and the C's, which it looks like the easiest one to start with will be the bending stress option. So our bending stress option, let's bring him down here and work with him. Option 1 for bending stress. So we found M, or well, let me do it this way. We have the allowable bending stress of, what was it, 9 megapascals. Moment is P over 2. I, we found I, it's over there. And then our C value, right? C value is distance from the centroid to the outer edge. And we know that distance is 125. It's the same value as the centroid. So I can go ahead and plug everything in. 9 megapascals equals P over 2 times 125 over 8.021 times 10 to the 7th millimeters to the 4th. So all of my units are in millimeters, right? This is newtons per millimeter. Whoops, I move that over a little bit. Just make a note of that. 9 megapascals is newtons per millimeter squared. So millimeters, everything's in millimeters. My load will come out to be in newtons. So here I get a maximum P value of 11550 newtons. So that's my max P value to have an acceptable bending stress. Now I need to check if this number is lower or higher than my other two options here. So I still need to check the shear stress and the shear flow options. All right, so one done. Let's take a look at option 2. Option 2, the shear stress option. So we have the allowable shear stress, 1.5 megapascals. We know V is P over 2. We just need that Q value, right? We know T. T for the maximum shear stress is, of course, at the neutral axis. That would be this line right here. T is going to be 25 millimeters. That's the thickness there at our neutral axis. So we just need the Q value. Again, the highest value of Q we can have is everything above the neutral axis. Here's our neutral axis. Here's our area of interest. Q is y tilde A. And here, this has a height of 100. This has a height of 25. This is, again, 100. And I think the thickness here is 25. So that's our Q. our centroid for our bottom rectangle here is 50, right? Half of 100 is 50 times the area, which is 25 times 100, plus the top has a centroid of, we found that earlier, 112.5, 112.5 times the top area, 100 times 25. So that I get a Q value of 406,250 millimeters cubed, just from plugging that into my calculator. So now I have everything I need for this one, so I can go ahead and plug in, what was my shear stress? 1.5 megapascals, so 1.5 newtons per millimeter squared equals P over 2 times my big Q value, 406,250, over moment of inertia, 8.021 times 10 to the 7th, times T, just 25. So again, everybody's in millimeters and newtons, so my P is going to work out to be in newtons. And here I get a P value of 14,808. 14,808. So for our option 2, we see that our shear stress option is actually bigger. And what that means is that the shear stress, it has more allowable shear stress, which means it will fail first under bending, right? As soon as we go up and up and up, loading more and more and more, loading, then we hit 11,550. Oh my gosh, get the words out. As soon as we hit that, that's where our bending stress fails. That's the max allowable load. So we don't even get to this second option, right? So this is not our max. This is not our limiting factor. But we have one more case to check. And that's the shear flow case. So in our shear flow case, right, we're gonna find our shear flow value and our Q. Now remember, this Q is not the same as this Q that we just calculated. This Q is the Q at the fastener, at the point where they're joined together. So for the shear flow, the Q uses this area here and does not include any of that center. Here's the neutral axis. So our large Q value, first moment of area, is only going to be that top portion. 1112.5 times 100 times 25. So that's 281,250 millimeters cubed. So that's our Q value for this one. Let's go ahead and move. Let's move these guys. I don't need these anymore. But I do want the S and the F. All right, let's go ahead and calculate our shear flow value. So shear flow, the lowercase q, is the allowable shear strength over the spacers, right, over the distance between them. So that'll be the 1,500 newtons over the, I think I want to keep it in millimeters. Yeah, I'll keep it in millimeters. 75 millimeters is going to give me 20 newtons per millimeter. 20 newtons per millimeter. So now I've got this 20 newtons per millimeter. I know what the shear is. I know what Q is. I know what I is. So I can say 20 newtons per millimeter equals P over 2 times the Q value we just found, 281,250, over moment of inertia, 8.021 times 10 to the 7th. And I do the very last step of plugging all of that into my calculator to get a P value of 11,407 newtons. 11,407 newtons, very, very slightly less than the P that we found with the bending stress, right? So only about 100 newtons less of force than the bending stress. So this shear flow is actually our limiting factor. And if we didn't want this to be our limiting factor, then we either need to get some stronger nails or we need to put those nails closer together. So this is our limiting factor in this one. The highest allowable stress that we can have is 11.4 kilonewtons. 11.4 kilonewtons. All right, so anytime you see allowable, if you have multiple allowables, think multiple maximums, multiple cases that you're going to have to check here. So these are all the steps that we're learning to piece together so that we can actually go ahead and design these things, right? As you go into your higher classes and as you go into work as an engineer, you'll actually be applying these things in these designs, right? As you design a beam.